The relative permittivity of a material is its absolute permittivity expressed as a ratio relative to the permittivity of vacuum. Permittivity is a material property that affects the Coulomb force between two-point charges in the material. Relative permittivity is the factor by which the electric field between the charges is decreased relative to vacuum. Likewise, relative permittivity is the ratio of the capacitance of a capacitor using that material as a dielectric, compared with a similar capacitor that has vacuum as its dielectric. Relative permittivity is also commonly known as dielectric constant, a term deprecated in physics and engineering as well as in chemistry. Definition. Relative permittivity is typically denoted as epsilon r omega, sometimes kappa or k, and is defined as epsilon r omega equals epsilon omega epsilon 0. Display style var epsilon underscore r omega equals frac var epsilon omega var epsilon underscore 0, where epsilon omega is the complex frequency dependent absolute permittivity of the material, and epsilon 0 is the vacuum permittivity. Relative permittivity is a dimensionless number that is in general complex valued. Its real and imaginary parts are denoted as epsilon r omega equals epsilon r omega minus I epsilon r omega. Display style var epsilon underscore r omega equals var epsilon underscore r omega I var epsilon underscore r omega. The relative permittivity of a medium is related to its electric susceptibility, chi-e, as epsilon r omega equals 1 plus chi-e. In anisotropic media, such as non-cubic crystals, the relative permittivity is a second-rank tensor. The relative permittivity of a material for a frequency of 0 is known as its static relative permittivity. Terminology. The historical term for the relative permittivity is dielectric constant. It is still commonly used, but has been deprecated by standards organizations, because of its ambiguity, as some older authors used it for the absolute permittivity epsilon. The permittivity may be quoted either as a static property or as a frequency-dependent variant. It has also been used to refer to only the real component epsilon r of the complex-valued relative permittivity. Physics. In the causal theory of waves, permittivity is a complex quantity. The imaginary part corresponds to a phase shift of the polarization P relative to E and leads to the attenuation of electromagnetic waves passing through the medium. By definition, the linear relative permittivity of vacuum is equal to 1, that is epsilon equals epsilon 0, although there are theoretical nonlinear quantum effects in vacuum that become non-negligible at high field strengths. The following table gives some typical values. Measurement. The relative static permittivity, epsilon r, can be measured for static electric fields as follows. First, the capacitance of a test capacitor, CO, is measured with vacuum between its plates. Then, using the same capacitor and distance between its plates, the capacitance C with a dielectric between the plates is measured. The relative permittivity can be then calculated as epsilon r equals C 0. Display style var epsilon underscore r equals frac C underscore 0. For time-variant electromagnetic fields, this quantity becomes frequency dependent. An indirect technique to calculate epsilon r is conversion of radio frequency S-parameter measurement results. A description of frequently used S-parameter conversions for determination of the frequency-dependent epsilon r of dielectrics can be found in this bibliographic source. Alternatively, resonance-based effects may be employed at fixed frequencies. Applications. Energy. The relative permittivity is an essential piece of information when designing capacitors, and in other circumstances where a material might be expected to introduce capacitance into a circuit. If a material with a high relative permittivity is placed in an electric field, the magnitude of that field will be measurably reduced within the volume of the dielectric. This fact is commonly used to increase the capacitance of a particular capacitor design. The layers beneath etched conductors in printed circuit boards (PCBs) also act as dielectrics. Communication. Dielectrics are used in RF transmission lines. In a coaxial cable, polyethylene can be used between the center conductor and outside shield. It can also be placed inside waveguides to form filters. Optical fibers are examples of dielectric waveguides. They consist of dielectric materials that are purposely doped with impurities so as to control the precise value of epsilon r within the cross-section. This controls the refractive index of the material and therefore also the optical modes of transmission. However, in these cases it is technically the relative permittivity that matters, as they are not operated in the electrostatic limit. Environment. The relative permittivity of air changes with temperature, humidity, and barometric pressure. Sensors can be constructed to detect changes in capacitance caused by changes in the relative permittivity. Most of this change is due to effects of temperature and humidity, as the barometric pressure is fairly stable. Using the capacitance change, along with the measured temperature, the relative humidity can be obtained using engineering formulas. Chemistry. The relative static permittivity of a solvent is a relative measure of its chemical polarity. For example, water is very polar, and has a relative static permittivity of 80.10 at 20 degrees Celsius, while N-hexane is nonpolar, and has a relative static permittivity of 1.89 at 20 degrees Celsius. This information is important when designing separation, sample preparation and chromatography techniques in analytical chemistry. The correlation should, however, be treated with caution. For instance, dichloromethane has a value of epsilon r of 9.08, 20 degrees Celsius, and is rather poorly soluble in water, 13 grams per liter or 9.8 milliliters per liter at 20 degrees Celsius. At the same time, tetrahydrofuran has its epsilon r equals 7.52 at 22 degrees Celsius, but it is completely miscible with water. In the case tetrahydrofuran, the oxygen atom can act as a hydrogen bond acceptor, whereas dichloromethane cannot form hydrogen bonds with water. This is even more apparent when comparing the epsilon r values of acetic acid 6.2528 and that of iodoethane 7.6177. The large numerical value of epsilon r is not surprising in the second case, as the iodine atom is easily polarizable. Nevertheless, this does not imply that it is polar. 2. Electronic polarizability prevails over the orientational one in this case. Lossy medium. Again, similar as for absolute permittivity, relative permittivity for lossy materials can be formulated as epsilon r equals epsilon r minus I sigma omega epsilon 0. Display style var epsilon underscore r equals var epsilon underscore r frac I sigma omega var epsilon underscore 0. In terms of a dielectric conductivity, sigma units s per meter, Siemens per meter, which sums over all the dissipative effects of the material. It may represent an actual electrical conductivity caused by migrating charge carriers, and it may also refer to an energy loss associated with the dispersion of epsilon, the real valued permittivity. P. 8. Expanding the angular frequency omega. 2 pi c, lambda and the electric constant epsilon 0. 1 micro 0 c2, which reduces to epsilon r equals epsilon r minus I sigma lambda kappa. Display style var epsilon underscore r equals var epsilon underscore r I sigma lambda kappa, where lambda is the wavelength, c is the speed of light in vacuum, and kappa micro 0 c 2 pi 59.95849 ohms approximately equals 60.0 ohms is a newly introduced constant units ohms or reciprocal Siemens, such that sigma lambda kappa equals epsilon r remains unitless. Metals. Permittivity is typically associated with dielectric materials, however metals are described as having an effective permittivity, with real relative permittivity equal to 1. In the low-frequency region, which extends from radio frequencies to the far infrared and terahertz region, the plasma frequency of the electron gas is much greater than the electromagnetic propagation frequency, so the refraction index N of a metal is very nearly a purely imaginary number. In the low-frequency regime, the effective relative permittivity is also almost purely imaginary. It has a very large imaginary value related to the conductivity and a comparatively insignificant real value. See also. References.